Good evening, everyone. Welcome to the second problem solving session for the course Environmental Remediation of Contaminated Sites. We'll wait for a couple of minutes so that if anyone wants to join, then we can start. We will start in 2 minutes. Hello, good evening. I welcome you all once again to the second problem solving session for the course Environmental Remediation of Contaminated Site. In week one, we have gone through a brief introduction about what are hazardous waste, and then we have seen the hazardous waste rules 2016, and then we have seen how this rule came. So then we have seen that some modification has come in 2016, and then we have learned about risk and hazard identification. We have seen two examples. I think was one of them was on landfill. So we have seen how to find out the risk from by taking the example of landfill, which was causing some contamination in the groundwater, and then we have moved to the second week. The second week, the brief recap of the first second week was already in the first week for the calculation of hazard and the risk. So in second week, so there are 5 lectures. So I think the first 2 lectures are based on. Just give me a minute. So the first 2 lectures are on dose response. So the first lecture is on the deterministic approach, and the second lecture was on the stochastic approach. So which takes into account the statistics. So if we have to find the risk for a very large population, which is also correct, because greater the number of population we will take, we will be able to take we will able to more accurately analyze the risk for a larger population. So in stochastic approach, we have seen numerical through which in which we were applying Monte Carlo simulation, and through that we were finding the risk. So sir has explained numerical based on this approach. So we have seen probability distribution function, and then how to solve a numerical uh, numerical by applying Monte Carlo simulation, and we have seen that in by solving a question through in the Excel sheet. And then the fourth lecture was also a bit half of the lecture was continuation of the numerical which was being solved in lecture 3. And then we have seen no, the again we have gone through the rules, that is the hazardous waste management rules. We have then moved to TCLP test, that is the toxicity characteristic leaching procedure test. So through TCLP test, we classify any waste as hazardous or not. So there are other tests like TCLP test. So, but in TCLP test, we take some waste. It can be a solid waste, or it can be a combination of solid and liquid waste, or it can be a liquid waste. We take the waste, and then we add some extractant solution, which is generally acetic acid or acetic acid in combination with NOH, and then we shake the waste with along with the extractant solution for around 18 to 20 hours, and then we analyze the contaminants like heavy metals, which was, I think it was, we were on the fourth lecture. So the fourth lecture is on the TCLP test. So we have seen what is TCLP test and how to briefly how to do the TCLP test. And the last lecture, it was on the waste management rules. So various waste management rules like plastic waste management rules, biomedical waste, e-waste, construction and demolition waste, and other waste like solid waste management rules 2016. So here we have basically seen the rules related to the hazardous waste rules, and how to manage the hazardous waste. We will discuss those. And then finally, this was all for the week 2. And then now let me share my screen to go through the lectures. Okay, so just give me a second. So it is on day dose response curve for the deterministic approach. So let's move. So in this curve, we can see that as the dose is increasing, so the percentage of population giving positive response is increasing. So for the cancer risk assessment, we take that at some at lower concentration also there will be some risk, but for non-carcinogenic analysis, this type of model can be taken where there is a where we can see some evidence of risk at some threshold level of contaminant concentration, which is known as NOA, that is no observed adverse effect level, and low observed adverse effect level. So, and as per US EPA, it has classified various pollutants on various groups. So, the group A is the human carcinogen. So, these are the pollutants which have where there is evidence for carcinogen effect on the humans. Then there are class B, which can be probable human carcinogens, and class C are the possible human carcinogens. There can be chances of carcinogenicity from these compounds, and class D are not classified as human carcinogenicity, and E does not have any evidence of carcinogenicity in humans. So again, these are the dose response relationship for the non-carcinogen. So I think this graph was on week 1 assignment where we have to find out whether it is for carcinogen or non-carcinogen. So this is for non-carcinogen, because in carcinogenic effect we take some sort of risk or effect at lower concentration also. But in non-carcinogen we can take it. There can be some limit above which the severity or response is seen. So NOAEL is the threshold, or we can say the concentration where no adverse effect is seen, and LOAEL is the low observed adverse effect level. So at above this level, very high severity or effect is seen, and below this level, the effect is not that much as compared to above it. So again, so there are some uncertainty factors or safe level which we take, and it is the safe level is given as LOEL or NOEL divided by uncertainty factor. So for since we are doing the trials on animals, so we have to take lot of safety factor into account. So 10 is taken for human variability, and because there are different types of people, some have high body weight, some has low body weight, some are very much reactive to something and others are not, and 10 is taken for exploration of data from animals to humans because we are doing the trials on animals, and 10 is used for less than for use of less than chronic data because we do the trials for some limited period of time, so we do not have that much data for a very long time. That's why 10 again 10 10 is taken as safety factor for this factor, and then if we are using LOEL instead of NOEL, then again we need to apply a safety factor. So again go through these into the lectures. So now let's move to the part where okay. Let's move to the part of exposure assessment. So, exposure will depend upon how much concentration of the pollutant someone is exposed to, what is the frequency, like how many days or for how many number of hours per day you are exposed to that pollutant, and for how much time or how long, like 10 years, 30 years, 40 years, like that you will be exposed. So based on this we can find out the exposure, or also it is known as chronic daily intake, or we can also call it as intake. So intake is given as exposure concentration into intake rate. So it will be in terms of liters per day. If the pollutant is in the form of liquid form, it is in water. It will be in milligrams per kg if it is from coming from the soil. And we need to find out the exposure frequency, like how many days per years it will be exposed to, and then exposure duration, whether it is for 5 years, 2 years or 10 years, and divided by BW will be the body weight into A2 80, that is the averaging time. So for calculation of risk due to cancer, this averaging time will be for 70 years, because for cancer risk we take the lifespan, and if it is for cancerous pollutants, then we will take as per given in the example. So again, this is that only okay. So after finding the hazard identification, then we did the exposure assessment and dose response. So after all these three, then we can find out the risk because we have all the data required. So finally we can calculate the risk. So, if we have to find out the risk due to non-carcinogenic compound, then we find out the hazard index or quotient, which is taken as the intake rate divided by some reference dose. So, these reference dose are values which are already been given, and we find out the ratio of these two. And if it is less than 1, then it is considered that the hazard is not then it is in the safe range, and if this ratio is more than 1, then it is considered that that this pollutant will cause adverse effect on the human. And for the carcinogens, it is taken as a intake rate, or chronic daily intake into slope factor. Again, this slope factor has been found out for different compounds on the basis of the trials done, and this slope factor will be given. So we will have to multiply with the daily intake, and we can find out the risk due to that pollutant. We can find out the cancer risk due to that pollutant. And this reference dose for the non-carcinogens, these are find out based on NOEL or LOEL divided by some uncertainty factor which I've seen earlier. So again, an example is given, so we will skip this. So example for both carcinogen and non-carcinogen is given. So we will see examples while solving the numericals. So this was the first lecture. So the second lecture was based on So the second lecture, previous lecture was based on deterministic approach, and now next one is based on the stochastic approach, where through Monte Carlo simulation we can solve the question. So I think this part is also based on the deterministic approach, where this is the solution for the question we have seen in the previous lecture slide. So we'll skip these also. So deterministic approach has some limitation because we are doing the point estimates. We are not able to take into, like, we are taking the average body weight, and we are taking um which is 70 kg, but different people will have different body weights. So all these can be taken into account by doing the stochastic approach, in which we take the mean and standard deviation of everything, and then we can and then I think this is the last slide. And then through Monte Carlo simulation, we can find out. I think I'm having some problem in sharing the entire screen. Okay, so then we have seen stochastic approach, where again everything was explained through a numerical. So this was the problem where probability distribution for everything was given. So here we can see that the average body weight is given in terms of mean and standard deviation. So since we are taking mean and standard deviation, so it will give a more realistic risk for the contaminants. And also here we can see that the concentration of the pollutant is also given in terms of mean and standard deviation. So through Monte Carlo simulation, we can find out the risk due to a contaminant, and this will be a more realistic approach, because we can find out the risk for a larger population, because we are not doing any calculation by hand. We can do it in Excel, and we can finally calculate the risk due to a pollutant. So now let's move to the fourth lecture. So again, I think half of the part of the lecture was about the numerical through to find out the risk through Monte Carlo simulation. So we'll skip those. It's taking some time to load the slides. So then we have seen the rules for hazardous waste management 2016 rules, in which we have seen the TCLP test, that is the toxicity characteristic leaching procedure test. So here limits for various pollutants are given. So we have seen say like for arsenic, after the TCLP test, the concentration of arsenic in the extractant solution should not be more than 5 milligrams per liter. And if the concentration of arsenic is more than 5 milligrams per liter, then that particular waste is hazardous, and it needs to be disposed as per the hazardous management rules. So if after doing TCLP test any of these contaminants is more than the limit, then the waste will be considered as hazardous. So we have limits for various metals, and also there are limits for various pHs, organic compounds also. So what happens in TCLP test? So acetic acid is taken. So suppose we have some solid waste. So we take the solid waste, then we have to reduce the particle size to, I think, less than 9 mm or 8 mm. So I'm not remembering the value of the particle size. So 9 mm. So we have to reduce the particular size of that waste by crushing. So we can use a mortar pestle, or we can crush in the grinder. So we have to reduce the particle size, and then we will take the extractant solution. So before taking the extractant solution, we first find out how much pH will be reduced of the waste by shaking or stirring the waste in DI water, and then we add some HCl, and then we find out what is the pH drop, and if the pH drop is not is less than 5, then we use extractant solution, which is consist of acetic acid and NOH, that is sodium hydroxide. And if the pH of the after adding HCl is more than 5, then we use the extractant solution, which only consists of acetic acid. And then what we do is we take the solid to liquid ratio of 20 is to 1. So suppose we have taken 1 gram of solid, then we need to add 20 ml of the extractant solution, and then we shake the sample into end over end shaker, like we give two or three, we give the whole complete rotation of 180 degree, and 360 degree, and after 18 to 20 hours we filter the sample and we analyze for the heavy metals and other contaminants, and find out whether it is passing the TCLP test or not. If the if it fails the TCLP, say, and if the waste or some sample fails the TCLP test, then it means the waste is hazardous and it cannot be used for any other purpose, so it need to be disposed of safely as per the hazardous waste rules. So then this is the last lecture, and the last lecture is about the various rules for waste management in our country. So here we can see the slide where there are various rules mentioned. So here we can see the plastic waste management rules, and then we can see the electronic waste management rules, biomedical waste rules, construction and demolition waste management rules. And we are mainly concerned about hazardous and other waste rules 2016, and and the other rule, which is the solid waste management rules. So the hazardous waste management rules ensures the safe handling, generation, processing, treatment, package, storage, transportation, use, reprocessing, collection, conversion, and offering for safe sale, destruction, and disposal of hazardous waste. So all these points are taken care by the Hazardous Waste Management Rules 2016, and it first came into effect from in the year 1989. So next we will see now there are some details about how to manage the waste. Like here we can see some data about what are the how hazardous waste generation has changed with years, and here we can see that uh, the number of industries producing hazardous waste has increased, and also the total waste generated, hazardous waste generated, has increased with each passing year. And also we can see that the budget allocated for management of these waste has also increased. So it is very important to manage the hazardous waste. And then that slide. So these are some of the salient features of the 2016 rules. So now the waste management hierarchy. So first is the prevention, next is minimization. The waste, it is like that the waste generation should be very less, and then whatever is being generated, the first choice is should be reused, and if it is not able to be reused, then it should be recycled, or if not recycled, then all the useful material should be recovered, or it can be co-processed with other waste. And finally, if it has gone through all the above steps and there is nothing that can be extracted or reused, then again it should be sent for safe disposal in the landfill designated for hazardous waste disposal. So again, there are some of the salient features of the 2016 rules, so please go through all these in the lecture slides. Now we can, I think, go to the question part. So the questions for this week, we have some numericals and some objective type questions. So I have also added few numericals from my end. So we will try to solve all those. So now let me share my other screen. So let's go directly to the first question. So the first question is, which of the following is incorrect regarding hazard identification and dose response study? So the first option is select human data over animal data. B is select animal species with least similar physiological response as compared to that in humans. C is apply linearized multi-stage model for low dose exploration, or D use animal data when human data is inadequate. So we have to find out of the four, which of the following points are incorrect. So again, I'll give you all 3 minutes. Just take your time, write the option in the chat box, and then we will discuss which one is the correct. So we have to find out the incorrect statement. So the first statement, select human data over animal data. So this is correct because if human data is available, we should use that. Next one is select animal species with least similar physiological response as compared to that in humans. So this is wrong. We should select animal species which have a maximum similar physiological response with the humans. So B is incorrect. C is apply linearized multi-stage model for low dose exploration. So this one is correct. We use multi-stage model. And next is the use animal data when human data is not when human data is inadequate. So D is also correct. So B is the incorrect statement. So B is the correct option for the first question. Now let's move to the second question. So the second question is, in a study conducted in a highly polluted city, a linearized multi-stage model was employed to assess the relationship between PM 2.5 concentration and the occurrence of cerebrovascular damage, stroke, and neurological damage to the brain. So the findings reveal that at a PM 2.5 concentration of 25 micrograms per meter cube, there were 10 cases of cerebrovascular and neurological damage per 10,000 individuals. If the current PM 2.5 concentration is 375 microgram per meter cube, it might be inferred based on linearized dose response model that the likelihood of experiencing heart stroke and brain damage could potentially increase to 150 cases per 10,000 individual. So in this question, we have been given like earlier when the concentration of PM 2.5 was 25 micrograms per meter cube. So the effect was that there was 10 cases of damage to nerves and brain per 10,000 individual, and when the concentration has increased to 375, the adverse effect has increased to 150 cases per 10,000 individual. We have to write whether this statement is correct or not. So please try to solve this question and then we will see how to do this, whether we have to write whether this statement is true or not. So again, I'll give you all 3 minutes. Just take your time and try to solve this question and then we will see. So let's try to solve this question. So initial concentration of the pollutant is 25 micrograms per meter cube, and the final concentration of the pollutant is 375 micrograms per meter cube. So here we can see that a linearized multi-stage model is used. So since this is linear relationship, so the increase in the concentration of the pollutant should be directly or linearly linked with the increase in the damage to the individual. So let's find out how much in terms of percentage, how much there is increase in the pollutant concentration. Increase in PM 2.5 in terms of percentage. So that will be the C final minus C initial divided by C initial into 100. So that is 375 minus 25 upon 25 into 100. So this is 1400 percentage increase. So this much percentage increase should be seen in the increase in cases of damage to brain and heart. So earlier there were 10 cases per 10,000 individuals. Now it will be 1400 percentage increase in cases. So that will be 10 into 1400%, that will be 4 divided by 10, that is the increase will be 140 cases per 10,000. So earlier so the potential increase will be already there were 10 cases per 10,000, and with 1400% increase the increase in cases has increased to 140. So this will be 150 cases per 10,000 individuals. So, the option A is correct, that yes, the statement is correct, that when the concentration was 25 micrograms per meter cube, there were 10 cases. When the concentration has increased to 375 micrograms per meter cube, now there will be 150 cases of damage to brain and heart per 10,000 individual. So, statement A is the correct statement. So, now let's move to the third question. So the question is, select the correct option regarding deterministic approach. The first option is it needs considerable amount of data in comparison to stochastic approach. Next is, minor drawbacks of this method is that it is resource and time consuming. Option C is it uses point estimate for the variable. And the last option is we only use reference dose in this approach and never use slow factor. So we have to select the options which are correct as per the deterministic approach. So again, I will give you all 3 minutes. Just take your time and write the option in the chat box, and then we will discuss which option, which of the following options are correct. So let's see which is the correct option. So the first is it needs considerable amount of data in comparison to stochastic approach. No. The data required for deterministic approach is less than as compared to um, stochastic approach. Next is minor drawback of this method is that it is resource and time consuming. No, it is not that much resource and time consuming. Next is it uses point estimate for the variable. So this is correct because we have average body weight. We take the average concentration. So everything is the average value. So that's why it uses the point estimates. Like we do the risk or find out the hazard in hazard question at various points based on the data given. And the last is we only use reference tools in this approach and never use slow factor. So this is not correct. Whether we need to use reference tools or slow factor, it depends whether we want to find out the hazard index or the cancer risk. So it is nothing to do with the deterministic or stochastic approach. So D is also the incorrect option. So only C is the correct option. Now let's move to the next question. So the question is, what is the primary objective of the TCLP test? So the first option is to measure the change in porosity of soil with variation in temperature and soil pH. Option B is to measure only pH of soil. C is to determine the mobility of contaminants. Or D is to determine the acidity of waste materials. So again, I will give you all 3 minutes. Just take your time. Try to solve this question like it is a theoretical question. So please try to write the correct option in the chat box and then we will see which one is the correct. So let's see which is the correct option. So TCLP test is Then to find out the mobility of contaminants. So first option, that it is used to find porosity of soil with variation in temperature and soil pH. This is incorrect. Second option, to measure only pH of soil. This is also incorrect. And the third option, which is to determine the mobility of contaminants. So this one is the correct. And the last option, which is to determine the acidity of waste material. So this is also incorrect. So C is the correct answer. Now let's move to the next question. So this is a numerical question, numerical based question. So we have to find out the hazard index. So the groundwater at a specific location has been affected by leachate originating from a nearby landfill containing the following compounds. So the leachate has cadmium, lead and mercury. So we have given the reference doses for these, and also the daily intake for these three contaminants are given, and we have to find out the hazard index. So again, I will give you all 3 minutes. Please try to solve this question and write the value which you are getting in the chat box. So let's see how to solve this question. So we have given three contaminants, its reference dose and daily intake has been given, and we have to find out the hazard index. So we know that hazard index is the ratio of daily intake to the reference dose. So hazard index or hazard quotient, it is the ratio of daily intake to reference dose. That is DI to RFD. So now let's find out for cadmium. First, let's find out for cadmium. So hazard index will be, we have daily intake of 8.5 into 10 raised power minus 2 milligram per kg per day, and the reference dose is 4.5 into 10 to the power minus 4. So on solving this, we are getting value of 188.89. Now let's find out the hazard index for lead. So for lead, again the given daily intake is 1.62 into 10 raised power minus 2 upon 6.8 into 10 raised power minus 6. So on solving this, we are getting the value of 2382.36. And for mercury, hazard quotient will be daily intake is 7.5 into 10 raised power minus 3, and the reference dose is 3.2 into 10 raised power minus 3. So it's coming out to be 2.35. So the hazard index for the overall contaminants will be sum of the hazard index for 1, 2 and 3. So hazard index for all the contaminants will be the summation of a hazard index for each contaminant. So it will be hazard quotient 1, hazard quotient 2 and hazard quotient 3. So the one is 188.89. Second one is 2382.36. And due to mercury, the hazard index is coming out to be 2.35. So on summing this all, we are getting value of 188.89 plus 2382.36 plus 2.35. So we are getting the value of 2573.6. So this is the hazard index due to all the three contaminants given, and since it is greater than 1, so there will be sufficient or the effect or adverse effect due to these contaminants will be seen in human population. So we get the hazard index as 2573.6. So this is the solution for this question. Now let's move to the next question. Okay. So there are two questions. So let's try to first solve the question number 6. So the question is, which statements accurately characterizes the stochastic risk assessment approach? So the first statement is, this method assumes that all input variables are known and fixed without considering uncertainty or randomness in the system. Option B is, utilizes random variables and probability distribution to model uncertainties. Option C is it is resource and time consuming, and option D is applicable only for carcinogen. So, with respect to the stochastic risk assessment approach, we have to find out which of the following statements are able to characterize it. So, again, I'll give you all 3 minutes. Just take your time and try to solve this question, and then we will see which of the following options are correct. So, let's see which of the following four options are correct. So, we have to find out which of the following characterizes the stochastic risk assessment approach. So, the first option, that this method assumes that all input variables are known and fixed. So, this is not correct, because in this approach we take the mean and standard deviation of the variables. So, these are not fixed. And we consider the uncertainty or randomness in the system, because we take the find out the probability distribution function, and then we find out the risk. So A is not correct. B is it utilizes random variables and probability distribution to model uncertainties. So this is correct. And C, it is resource and time consuming. Yes, it will be resource and time consuming. And the third, that is, it is only applicable for carcinogen. It is not correct. It can be applicable for carcinogenic and non-carcinogenic compounds as well. So B and C are the correct option. Now let's move to the next question, which is question number 7. So the question is, which option is correct regarding TCLP test? So the first is waste or the particle size should be less than 9 mm. Tumbler is mixed N over N for 18 hours. And next C is we choose acetic acid because it is what we expect to be formed in a municipal waste dump site, or D, all of the above. So we have to find out which of the following are correct options. So again, I will give you 3 minutes. Just take your time, write the option in the chat box, and then we will discuss the question. So let's see which of the following option are correct. So first is waste or particle size should be less than 9 mm. So this is correct for doing the TCLP test. If the particular size of the waste is more than 9 mm, then we need to crush it and bring it below 9 mm. So the next is tumbler is mixed end over end for 18 hours. Yes, this is done. So end over hour shaking is done to achieve equilibrium in 18 to 20 hours. And C, we choose acetic acid because it is what we expect to be formed in municipal waste dump sites. So this is also correct. So because in municipal waste dump site, after the capping of because every day the waste is placed in the cells, it is covered with soil. So and slowly whatever air will be inside the waste voids, that will be consumed by the microbes present, and finally after few years of some time the microbial system or microbial degradation will shift from aerobic to anaerobic. And as we know that during anaerobic degradation methane is produced, and one of the steps for the methane production is the acetic acid production. So one of the intermediates is acetic acid. So since acetic acid will be formed, so and we know that at acetic pH, majority of the metals are in the dissolved form. So the heavy metals and other contaminants, they will dissolve and come out, and they will come out in the leachate. And so that's why we use acetic acid to do the TCLP test, because any waste, if we consider it as non-hazardous, that will be go to the municipal waste dump site, and after some time during the anaerobic degradation, acetic acid will be produced, and the contaminants present in that waste will come in the form in the leachate, and they will contribute to the pollution. So that's why we take acetic acid. So D, that is all of the above option. D is the correct for this question. Now let's move to the next question. So the question is, which of the following rules were promulgated or passed recently? A. Plastic waste management rules 2016. B. E-waste management rules 2016 and biomedical waste management rules 2016. C. Hazardous and other waste primary management and transboundary movement rules 2016, or D, all of the above. So we have to find out of the these four rules, which of the following has been passed or promulgated recently. So again, I will give you all 3 minutes. Just take your time, write the option in the chat box, and then we will see which one is the correct. So let's see which of the following options are correct. So the plastic waste management rules, yeah, electronic waste management rules, biomedical waste management rules, hazardous waste management rules, all these four rules are passed recently. So all of the above will be the correct answer. So now let's move to the next question. So this is a numerical type question. So we have to calculate the risk due to the following carcinogens. So we have been given three pollutants, chlorobenzene, benzene, BHP, and the corresponding slow factor is given. And average intake of the pollutants has been given. So we have to find out the risk. So again, I will give you all 3 minutes. Just take your time and try to solve this question and write the value which you are getting in the chat box. So Swam, please try. So I have given this question. Please try to solve this question and write the value which you are getting, and then we'll try to see how to solve this question. So let's see how to solve this question. So we have been given the average intake, that is the daily intake has been given, and we have been given the slope factor. So the risk of cancer for any pollutant is given as average intake into the slope factor. So let's find out for each pollutant, and then we will sum the risk of all the pollutants to get the overall risk. So risk is given as average intake into slope factor. So let's find out the risk first for chlorobenzene. So risk will be 1 into 10 raised power minus 9 into 6.1 into 10 raised power minus 3. So it will be 6.1 into 10 raised power minus 12. Next is for benzene. So risk due to benzene, it will be the average dose or intake is 3 into 10 raised power minus 8 into the slope factor is 3.8 into 10 raised power minus 4. So this will be 11.4 into 10 raised power minus 12. And for BHP, no slope factor is given. So since the data is not given, or maybe from BHP there would be no risk of carcinogenity to humans. That's why that is given as not any. So because of BHP, there will be no risk. So overall risk will be summation of risk for benzene and chlorobenzene, so which is 6.1 into 10 raised power minus 12 plus 11.4 into 10 raised power minus 12, which is coming out to be 17.5 into 10 raised power minus 12. So here the risk will be 17.5 into 10 raised power minus 12. So this is the risk due to all these pollutants given. So now let's move to the next question. So the question number 10 is the hazardous and other waste management and transboundary movement rules 2060 is not applicable to. So the first option is wastewater and exhaust gases. Next is biomedical and radioactive waste. C is waste arising out of the operation of ships beyond 5 km of the baseline, or D, all of the above. So we have to find out of all the following types of waste, on which of the following waste hazardous waste management rules 2016 is not applicable. So please take your time and write the option in the chat box, and then we will discuss. So let's see which of the following options are correct. So waste, water and exhaust gases. So hazardous waste management rules will not be applicable here. Biomedical and radioactive waste, they have separate rules. So similarly, wastewater and exhaust gases, so they have different rules. And waste arising out of operation of ships beyond 5 kilometers of the baseline, so they have also different rules. So all of the given types of waste, so hazardous and other waste management rules 2016 is not applicable to all the types of waste given. So D will be the correct answer, because in the question it is we have to find out of the following waste, in which of the following waste 2060 rule is not applicable. So for all the waste 2016 rules is not applicable. So let's move to the next question. So the question is, the highest dose that has no harmful effect on a population is known as NOEL, NOEL, NOAL or NOPA. So again, I'll give you all 3 minutes. Just take your time, write the option in the chat box, and then we will see which of the following are correct. So the highest dose that has no harmful effect on a population due to a pollutant is NOAEL, that is no observed adverse effect level. So A is the correct option. So now let's move to the next question. So the question is, according to the graph, low death is observed at low concentration. So we have to say whether the statement is true or false. So again, I will give you all 2 minutes. Take your time and write the option in the chat box, and then we will discuss. So let's see whether the statement is correct or not. So the statement is the low death is observed at low concentration. So here we can see that when the dose is lesser, log of the dose is lesser, we have lesser that. And when we are increasing the dose, so the mortality rate has increased substantially, and then it is going towards saturation. So this statement is correct that at lower concentration we have lesser death. So A is the correct answer. Now let's move to the next question. So the question is the mean concentration of 1,2-dichlorobenzene in a water supply is 1.7 grams per liter. Determine the chronic daily intake for a 70 kg adult. Assume that 2 liters of water are consumed per day. So we have to find out the chronic daily intake, and everything is given. So I will give you all 3 minutes. Just take your time, try to solve the question, and then we will see what is the correct answer. So let's see how to solve this question. So we have to find out the daily intake, and we know, I think I have added the slide. So the intake, we can find out, we have given the concentration. This concentration was given in, I think, grams per liter. So we have been, so this is in water. So water intake rate has been given. I think that was 2 liters per day. So we'll multiply it with, so I think there will, no conversion factor will be required. So let me write the formula here. So chronic daily intake, it will be C, that is concentration of the pollutant, multiplied by CF, no, sorry, EF, that is exposure frequency, sorry, so intake rate of the pollutant, ingestion rate, I think, multiplied by exposure frequency, multiplied by exposure duration, divided by body weight into averaging time. So from the question, concentration is given as, I think it was 1.7 grams per liter. Okay. I think this was in micrograms. So let's convert it into micrograms. So 1.7. To convert it into milligram, we will divide it by 1000. So this was milligrams per liter. So that will be 0.0017 milligrams per liter or ppm. So ingestion rate or intake rate is 2 liters per day. Again, exposure frequency it is, so it's in water, so it will be for 365 days. So any person consumes water every day, so it will be 365 days per, sorry, uh, okay, 365 days per year. Okay, exposure duration. So let's take the exposure duration as 30 years. So we will find out the intake for 30 years. So averaging time will be 365 days per year multiplied by 30 years. So this much will be our averaging time. So the chronic daily intake, when we substitute all these values, so chronic daily intake will be 0.0017 multiplied by 2, that is the uh, intake rate of the water, multiplied by exposure frequency, that is 365 days, multiplied by duration, that is 30 years, divided by body weight, we have been given 70 kgs, and the averaging time, it is 365 into 30. So let me calculate this. So it's coming out to be 4.857 into 10 raised power minus 5, I guess. Yes, into 10 raised power minus 5. So the unit here will be milligrams per kg per day. So this is the answer for this question. So the chronic daily intake. So we have been given the concentration of the pollutant, we have been given the ingestion rate, and we have been given the exposure frequency. So anyone drinks water for the entire, for every day, so it will be 365 days per year, and we have assumed the exposure duration as 30 years. So let me write here, exposure duration is 30 years. So for this we have to find out the chronic daily intake. So we put everything into the formula and we find out the chronic daily intake, which was coming out to be 4.857 into 10 to the power minus 5 milligrams per kg per day. Now let's move to the next question. So we have been given a drinking water supply is found to contain zero point 0.1 milligrams per liter of acetone and zero point 0.1 milligrams per liter of chloroform. A 70 kg adult drinks 2 liters per day of this water for 5 years. What will be the hazard index and the carcinogenic risk from drinking this water? So let me give everything. So assume the reference dose for acetone as 0.1 milligram per kg per day. So first find out the hazard quotient. So to find out the hazard index or quotient, first we need to find out the chronic daily intake or the average daily intake. So let's see how to solve this question. So and also the reference dose for chloroform is that is also 0.01 milligrams per kg per day. So let's first find for acetone. So the average daily intake would be, so we have just seen the formula here. So it is concentration given into the rate of ingestion into exposure frequency into duration divided by body weight into averaging time. So we have the concentration in the water as 0.1 milligrams per liter multiplied by ingestion rate, that is 2 liters per day, divided by body weight, that will be 70 kg. Into exposure duration, sorry, exposure frequency is 365 days per year, anti duration is 5 days. So and here the averaging time will be 365 into 5. So we are getting the average daily dose of 2.9 into 10 raised to power minus 3 milligram per kg per day. Similarly for chloroform, we will be finding the average daily intake as the concentration is 0.01, I guess. So the concentration is same for both. It is 0.1 only. milligrams per liter. Ingestion rate is 2 liters per day. Exposure frequency will be 365 days per year. We have to find out for 5 years. Divided by average body weight will be 70 kgs. And the averaging time will be for 365 into 5 years. So here also I think we are getting the same values because concentration is same and ingestion rate is also same. So we can find out the hazard quotient or hazard index as ratio of average daily dose divided by reference dose. So average daily dose for acetone is 2.9 into 10 raised power minus 3 divided by reference dose is 0.1, and for chloroform it is 2.9 into 10 raised power minus 3 divided by 0.01. So we are getting the value of 0.319. So since it is less than 1, so this traces of chloroform and acetone will be safe. Now we have completed the first part of the question, like we have find out the hazard index. Now we have to find out the carcinogenic risk from drinking this water. Okay, let me add a slide here. Okay, now we can do the further calculation here. So the risk is we multiply the chronic daily intake with the slope factor. So slope factor for acetone, for acetone, it is given as I think the so for acetone, slope factor is not given, and from chloroform, slope factor is 6.1 into 10 raised power minus 3. Now first we will find out the chronic daily intake. So chronic daily intake will be the concentration of the chloroform, that is 0.1 milligrams per liter, multiplied by ingestion rate, that is 2 liters per day, multiplied by exposure frequency, that is 365 days per year, multiplied by for how much is the exposure duration, that is 5 years, divided by body weight, that will be 70 kgs, and averaging time will be 365 days per year multiplied by 70 years. So since we find out the cancer risk for the entire lifetime of the humans, so that's why this will be the multiplied by 70 years. So the chronic daily intake we are getting as 4.19 into 10 raised power minus 5 milligrams per kg per day. Now we have been given, there is no slope factor for acetone, only for chloroform. So risk will be chronic daily intake into slope factor. So chronic daily intake is 4.19 into 10 raised power minus 5 multiplied by slope factor, which is 6.1 into 10 raised power minus 3. let me solve this. So we are getting 25.559 into 10 raised power minus 8. So we can convert this to 2.55 into 10 raised power minus 7. So since it is less than 10 point minus 6, so it is less than 10 power minus 6, the cancer risk is not that much. So this dosage is safe for cancer also. So the risk is within the safe limits. So these were the questions based on week 2 material. So we have seen how to find out the risk and hazard question based on deterministic and stochastic approach, and then we have discussed the TCLP test, and then we have discussed about the various rules for different types of waste, and main focus was on the hazardous waste management rules 2016. And then based on these material we have tried to solve few numericals and few objective questions. So these were the questions for today's session. So thank you so much for joining. Have a nice day, and we will meet on next Sunday from 6 to 8 p.m. to discuss the materials and questions based on week 3. So thank you so much for joining. Have a nice day.